Hi everybody, welcome to another video lesson. We are continuing graphing polar curves. We're going to graph polar equations today and analyze those graphs of polar equations using one more shortcut that we're going to look at. And then we're going to take a look at classical polar curves and how to identify those. So let's hop right in. Okay, we've been looking at symmetry to help us graph our polar curves, but now we're going to take a look at zeros and maximums. Because if you recall in previous lessons when we were graphing our trig functions, we used maximums and minimums and zeros to really quickly sketch, really accurately sketch graphs of trig functions, right? So now we're going to use those critical points along with our symmetry to really easily and really quickly graph our polar equations, okay? Let's see how we do this. If I have, it should be f of theta here. F of theta is equal to 2 cosine theta. So that's not an x, that is a theta. Okay, so f of theta is equal to 2 cosine theta. See, what we have here is when my trig function crosses the x-axis, okay, because this is Cartesian coordinates right here. Okay, so when that crosses the x-axis or our midline, that is when we're actually going to see that the polar equation crosses the pole at those same points, okay? So at theta equals 3 pi over 2 and pi over 2, 2 cosine theta is going to cross the pole as well, right? Now also, when we have points that are furthest from our midline, okay, thinking about our maximum and minimums, okay, and again, this is the x-axis, is our midline in this case, that is where we have our greatest R values, okay, on our polar equations graph, okay, our graphs in our polar coordinate grid. Okay, so when our R is maximum and when our R's are 0, we can pretty easily plot those points, okay? And whatever this value is, that is actually that greatest R value. So in this case, it goes up 1, 2, okay, so the amplitude is 2, and so the maximum R value in our polar curve would be 2, okay? So that is that concept. Let's also take a look at some classic polar curves here. We have circles first up, circles we know, and then we also have generic forms for each one of these. So we have R equals a cosine theta or a sine of theta. So if I see this type of equation, I know when I start graphing that it should be a circle, right? We also have a limacon here. That is a plus or minus b cosine theta or a plus or minus b sine of theta. And that's going to give us a limacon. And I know these are sort of specific, very different words. Okay, so if you see limacon or if you think limacon, limacons look like a leaf, right? Okay, so limacon, think leaf, and think these equations here. We also have roses. Roses have general equations of a cosine n theta and a sine n theta, which is similar to our circles. However, now n is going to be greater than or equal to 2, okay? So we have n greater than or equal to 2 there. That's going to give us roses, which these look like roses, right, when we graph these. And we actually call these petals, okay? Each of these would be a petal. Okay, so this graph would have 8 petals right here, all right? And then we also have what's called a lemniscates. Okay, when you see lemniscate, think figure 8. That looks like our little infinity sign. Lemniscates, figure 8. And this is the only one that has r squared equals a squared cosine 2 theta. Okay, so if you see r squared, or if you see, like if you were to graph this, you might need to put square root. Okay, you'd have to put plus or minus the square root here. So if you see that, you know that you're dealing with the lemniscate. Okay, and then our last shape here, the spiral of Archimedes. This is the only one that looks like a spiral like this. It's a very specific type of shape, and our general form is going to be r is equal to a theta. Okay. This is the only one that does not have some sort of trig function involved. Okay, it's just r equals a theta. Okay, plus b on that one. Okay, so let's go ahead and look at our symmetry zeros and max and mins. Okay, so if I have r equals 3 sine 2 theta, I can go ahead and graph this in my Cartesian xy axis. Okay, so and we can do this really quickly, right? And what I'm looking for now is going to be my zeros and then my maximums, okay? So at my zeros on this Cartesian coordinate grid, we know that it also intersects the pole at those points. So we're intersecting the pole at theta equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? So at these points, we are intersecting the pole. And my max R values, which in this case is going to be 3, right? Because our amplitude is 3. So this distance here from our midpoint, or our midline, to this maximum, and from the midline to the minimum, that's 3. Okay, so we are going to have max R values on our polar grid, our polar graph, at theta equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay. Now also, I know that this looks like R equals a sine n theta, where n is greater than or equal to 2, right? So that lets me know that we're dealing with a rose here, okay? We're dealing with a rose, and our n is 2, our a is 3. And if our n value is even, then that means we have 2n petals, okay? So 2 times n is the amount of petals that we have. If n is odd, then we just have n petals. In this case, it's even, so we have 2n, so we have 4 petals for this one. Okay. So with all of this information, we can go ahead and start graphing this. So again, we have max R values at pi over 4, 3 pi over 4, and then 5 pi over 4, and 7 pi over 4. Okay. So we can really quickly, boom, 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 we've already graphed 4 of our points here on our polar coordinate grid. Okay. So now we really just need to graph a couple more points, and really I chose pi over 6 and pi over 3 because I know that each one of these is going to be the maximum, the farthest point of a rose petal, okay? I know I have 4 petals. I've got 4 of these maximum R values, so each one of these is going to be a petal, right? So if I can find the coordinates for pi over 6 and pi over 3, then I can really easily mirror those for each one of my petals, because all my petals in this instance are going to be the same shape, okay? So that's pi over 6, that's 2.6 and 2.6. So then on either side of my pi over 4, angles, I can go ahead and plot a 2.6 and a 2.6, okay? And then I can go ahead and hopefully you can start to see this shape taking form. If I go ahead and connect my dots, I get a petal that looks like this, or a rose that looks like that, okay? Okay, so that's that, and let's go ahead and identify some of our classic curves here. We're going to identify the type of curve by each given equation. Okay, so again, R squared. Anytime I see this R squared, I'm thinking lemniscates every single time. Okay, and if you were to graph this, you would in fact get a lemniscate. All right, for R equals to theta, anytime there is no trig function, we know we have the spiral of Archimedes. And if you graph that, it looks something like this. Okay, this one's a little bit more difficult. I've got 3 plus 3 cosine theta. Okay, this looks like R equals A plus B cosine theta, which lets me know that we're dealing with a limacon. Okay, and this is actually a special case limacon because when A is equal to B, we have what's called a cardioid. Okay, cardioid. Make sure you write that down. Make sure you remember that one because that's a special type of limacon. A cardioid when A is equal to B. Okay, and a cardioid looks just like this. Okay, so that's it, guys. That's it for this video, identifying classics and using our max min values. Good luck with your practice.